Hi, my name's Jonathan, and I'll be taking you through the solutions to problem set 1, question 1. Now before starting any problem, it's always good to note what data you have. So as you can see, I've noted here what is given. We have been given the principal's utility function, which is equal to the output of task 1 plus the output of task 2 minus the wage paid to the agent. The agent's utility function is the wage minus half of the effort put in to task 1 squared plus the effort put into task 2 squared plus the effort put into task 1 multiplied the effort put into task 2. The principal's incentive scheme, another way of saying the wage paid to the agent, is equal to sum alpha plus beta x1, where again x1 is the output of the agent. You'll notice that it is only dependent on task 1 and independent of task 2. The output based on the effort levels in task 1 and task 2 is simply linear, where the output for task 1 is equal to the effort put in, and the output for task 2 is equal to the effort put in. So moving on to the question 1a. So before I begin, I like to rewrite the wage in terms of the effort levels E1 and E2. So as you can see, I've done there, wage now is equal to alpha plus beta E1. So in order to find the effort levels of the agent, we need to maximize the utility levels of the agent with respect to effort 1 and effort 2. So again, we substitute, rather than writing wage, we write alpha plus beta E1, because I've substituted, instead of writing x1, I'm now writing E1. And then all I do is take the partial derivatives of the agent's utility function with respect to E1 and E2. And in order to find a maximum, we make both of these equal to 0. Based on this, we can derive two equations, which I've called 1a and 2a, and solve them simultaneously simply by rewriting and rearranging them, as you can see there. Moving on to the next page and following the solution, we find that E2, the effort level into task 2, is equal to minus 2 beta over 3, and the effort level put in by the agent into task 1 is equal to 4b over 3. Now moving on to part B, the question asks us to find the principal's incentive scheme, that is, the alpha and beta values that result in the principal maximizing their utility function. So now before we start this question, we need to note that for the agent to want to perform the principal's task, we need the agent's utility to be greater than or equal to some outside utility that he would receive for not performing this task, which we call U0. That is to say that the wage minus the cost of performing the task is greater than or equal to U0. However, if we recall that the principal's utility function is equal to the outputs of the two tasks minus the wage paid to the agent, we would see that the principal would want to minimize the wage as much as possible in order to maximize his utility function. And as such, he's going to reduce the wage to the degree until the agent's utility is equal to his outside utility. In order to capture this restriction, we use a bit of a mathematical trick. And we say that the principal's utility function is equal to the principal's utility function plus 0. Substituting UA equals UO, or UA minus UO equals 0 into this, we derive an expression over here for the principal's utility function. Subbing in x1 equals E1 equals 4 beta over 3 and x2 equals E2 equals minus 2 beta over 3 into this expression, gives us an expression for the principal's utility function only in terms of beta. And what we also find is that the wages cancel out in this expression, and as such, this is independent of the wage, and alpha actually cancels out. Simplifying this expression, we obtain this expression over here, which is nice and simple. Now, in order to maximize the principal's utility function, we simply take the derivative of the function with respect to beta and make it equal to 0. We then find that beta is equal to 1/2. And it's important to note that if we take the second derivative of this, we get -4/3, which is less than 0, indicating that this is in fact a maximum for the utility function. To find alpha, we recall that UA is equal to UO. Substituting in for UA, we get this. And then substituting in the values for E1 and E2, we obtain this expression over here. Simplifying this expression in terms of beta, we obtain this simplified expression over here. Rearrange for alpha to obtain the answer that alpha is equal to U0 minus 2 beta squared over 3. Part C of this question asks us to find the effort levels put into the two tasks. And this is found very easily by substituting beta equals 1/2, which is what we found in part B. And we find that the effort put into task 1 by the agent is 2/3, and the effort put into task 2 by the agent is -1/3. And this can be interpreted to mean that the agent would take actions in the second task that would reduce the principal's payoff for that task. Part D asks us to find the efficient effort levels. Another way of understanding this question is, what are the effort levels that maximize total utility? That is, the utility gained by the principal as well as the agent. So substituting in the functions for the principal and agent's utility, we obtain total utility. Substituting in the effort levels that correspond to the output levels, we obtain a simplified total utility function in terms of effort levels 1 and 2. We then simply maximize UT with respect to E1 and E2 by finding the partial derivatives. We notice that in fact these two equations, 1 and 2, are symmetric. That is, E1 is equal to E2, and that helps us solve these quite quickly. Substituting back in and solving, we find that E1 is equal to E2, which is equal to 2/3. So we notice that what actually happens with regards to the effort levels is not, in fact, the efficient effort level outcome. So why is this the case? Well, firstly, it's important to notice that the total utility function is independent of the wage. Whereas when the agent calculates his effort levels that help him attain a maximum utility level, he does take wage into account, and this wage is in fact independent of the amount of effort he puts into task 2. As a result, we get that the effort 1 does not equal to effort 2, and in fact he only puts effort into task 1 because he's only rewarded for putting effort into that task. If, however, the principal was able to reward the agent for the amount of effort he put into task 2, for example introducing a beta 2 that is equal to beta 1, then the utility function of the agent would be something like this, where he receives a reward for the effort put into task 2. He would then maximize this utility function with respect to the two effort levels, and if beta 1 equals to beta 2, then we would get the symmetric result that we found in the previous question, and going through the maths we would find the efficient outcome, that is E1 is equal to E2, which is equal to 2/3. And accordingly, what this says is that the principal needs to incentivize the agent equally in both tasks in order to achieve the efficient outcome. So, what would happen if, as in part F, Vodafone offered to pay a bonus to their customer service representatives for quick resolutions only, and not for other tasks, such as the quality of the solution offered? Well, we can understand this as suggesting that Vodafone would pay them a wage that is equal to some fixed amount, plus a bonus that is based on task 1, E1, which I've defined here as the quick resolution. They are not, however, rewarded for a second task, which we might interpret to be the quality of the solution or service offered. Using the model, this would suggest that the amount of effort put into task 1 or quick resolutions would increase, whereas the amount of effort put into task 2, the quality of the solution or service, would decrease.